The astronomical community was sent reeling when Neil deGrasse Tyson dropped an unexpected bombshell about Neptune during a globally streamed symposium. The renowned astrophysicist, celebrated for making complex cosmic concepts accessible, stood before a packed auditorium and delivered findings that fundamentally challenged our understanding of this distant ice giant. For generations, Neptune had been textbook material, the solar system's eighth planet. Discovered through mathematical prediction in 1846 rather than direct observation, its blue gaseous nature confirmed by Voyager 2's brief 1989 flyby that revealed supersonic winds and massive storms. But Tyson's presentation, drawing on cutting-edge data from the James Webb Space Telescope combined with Earth-based interferometric arrays, painted a radically different picture. These sophisticated instruments detected gravitational anomalies, unusual electromagnetic signatures, and unexpected thermal patterns that contradict everything we thought we knew about ice giants. Where conventional models suggested an orderly layered interior, rocky core, icy mantle, and gaseous atmosphere, the new data reveals a turbulent, chaotic world with plasma-like zones and mysterious hotspots defying thermodynamic expectations for a planet so far from the sun's warmth. The implications are profound. Neptune's internal structure appears to be a dynamic, churning mosaic rather than the stable, differentiated layers we've long assumed. These findings don't just rewrite Neptune's story, they force us to reconsider fundamental assumptions about planetary formation and behavior in our solar system's coldest reaches. What we're seeing suggests energy generation and material movement processes that current models simply can't explain, hinting at undiscovered physics operating within these distant worlds. The mystery of Neptune's unexplained heat sources deepens when we consider its position in the solar system. At such an extreme distance from the sun, solar radiation is far too faint to generate significant warming, and none of Neptune's moons are large enough to create substantial tidal heating through gravitational interactions. This leaves only one plausible explanation. Some unknown internal process is producing far more thermal energy than our current planetary models can account for. Even more baffling are the new revelations about Neptune's magnetic field. While scientists already knew the planet's magnetic field was strangely tilted and off-center, the latest data shows it's not just unusually positioned, but fundamentally unstable. The field appears to be in a constant state of transformation, with entire sections drifting and reorganizing in cyclical patterns never before documented in planetary science. This bizarre behavior has forced researchers to completely rethink how Neptune generates its magnetic field. Unlike Earth's relatively stable field, created by our planet's molten iron core, or Jupiter's powerful dynamo driven by metallic hydrogen, Neptune may possess an entirely different mechanism. Current theories suggest a shell of exotic, super-pressurized ices could be undergoing complex chemical reactions, creating electrical currents that power this unpredictable magnetic dynamo. When Tyson presented this radical possibility to the assembled scientists, the room erupted in astonished whispers, recognizing the profound implications for our understanding of planetary physics. The most startling possibility emerging from these findings suggests Neptune's interior may contain vast hollow spaces or stratified chambers, essentially acting like cosmic resonance chambers for electromagnetic and gravitational energy. While still theoretical, this radical concept could completely transform planetary science. Such an unconventional internal structure would make Neptune behave fundamentally differently from the standard models of either solid planets or gradually compressed gas giants. The implications are staggering. If Neptune truly possesses such exotic architecture, we may need to rewrite our understanding of the solar system's formation. Current theories already suggest Neptune didn't form in its current position, but migrated outward, reshaping the Kuiper Belt and possibly ejecting another giant planet in the process. But if Neptune itself is more complex and dynamic than we imagined, the early solar system's history may have been far more turbulent than we've ever conceived. Adding to the mystery, Tyson revealed the detection of bizarre radio emissions coming from deep within Neptune. While planets naturally emit radio waves from atmospheric interactions, these signals appear to originate from the planet's interior and display patterns unlike any known natural phenomena. Researchers are now investigating whether these emissions could reveal quantum-level behaviors occurring under Neptune's extreme pressures, entirely new states of matter formed by exotic chemistry, physical processes never before observed in nature. The discoveries keep compounding. Preliminary data even suggests Neptune's atmosphere may contain exotic materials previously only created in laboratory settings. Each new finding paints a picture of a world far stranger and more complex than the simple ice giant we thought we knew. Tyson presented compelling evidence that Neptune may contain vast quantities of supersonic ice, an exotic state of matter where water molecules break apart under extreme pressure, creating an electrically conductive slush that behaves paradoxically as both solid and liquid simultaneously. This bizarre material could solve multiple mysteries at once, potentially explaining Neptune's unexplained heat signatures, peculiar electromagnetic activity, and even contributing significantly to the planet's overall structure. Current models suggest these supersonic ices might circulate in massive, slow-moving currents deep within the planet, generating complex fluid dynamics far more intricate than anything observed in Jupiter's atmosphere or Earth's oceans. The discussion then turned to Neptune's supersonic winds, which scream across the planet at 1,300 miles per hour, faster than a jet fighter. While conventional explanations pointed to atmospheric heating patterns, new data suggests these tremendous winds might actually be driven from within, powered by deep-seated thermal pulses or even phase changes occurring in the planet's exotic interior. If confirmed, this would make Neptune the first known planet whose weather systems are primarily energized by internal processes rather than external solar heating, a revolutionary concept in planetary science. These revelations carry profound implications beyond our solar system. Among the thousands of exoplanets discovered by missions like Kepler and TESS, so-called mini-Neptunes represent one of the most common planetary types. If our own Neptune defies existing classification, astronomers may need to completely reconsider how we model these distant worlds, potentially overhauling our understanding of their composition, internal structure, and even potential habitability. Perhaps most provocatively, Tyson floated the radical idea that Neptune might represent an entirely new category of celestial object, something straddling the line between planet and failed star. While far too small for nuclear fusion, Neptune's unexpected internal heat and dynamic energy systems suggest it may belong to a previously unrecognized class of astronomical bodies that challenge our traditional planet-brown dwarf binary. This would fundamentally expand our cosmic taxonomy, revealing a universe with far greater diversity in planetary architectures than we ever imagined. Tyson poetically described Neptune as a chaotic system in perfect equilibrium, not a quietly cooling world, but one crackling with mysterious internal energies that maintain its turbulent balance. These groundbreaking insights were only made possible by cutting-edge tools like JWST and next-generation ground arrays, proving that every leap in observational technology brings new cosmic revelations. As our instruments grow more sophisticated, we're likely to discover more Neptunes, worlds that defy expectations and force us to rewrite the textbooks. The coming years may see heated debates about scientific models as we grapple with these paradigm-shifting discoveries about our own solar system's most enigmatic giant. Who could have imagined that Neptune, long considered the solar system's quiet, frozen outpost, would emerge as potentially the most bizarre world in our cosmic neighborhood? This stunning revelation serves as a powerful reminder. If a planet in our own backyard can shatter expectations so completely, what other surprises await in the vast unknown? Tyson's groundbreaking announcement transcends astronomy. It speaks to humanity's endless curiosity, science's willingness to question its own assumptions, and the exhilarating reality that every discovery can rewrite what we thought we knew. We'd love to hear your thoughts on these cosmic revelations. Could Neptune's secrets change how we understand our solar system? What other surprises might be lurking in the outer darkness? Drop your reactions in the comments below.